will share the link and where we have our other presentations too. But yeah, I'm very excited regarding your work. Okay, so I believe we can start. Sandeep, can you confirm the recording is going on? Just a secondary eyes. Okay, because I'm on a web browser. Thank you, Linux and Teams. Okay, so let me start. So, good morning, everybody. Today we have the honor of inviting Professor Patricio Vela for our AVIAT seminar. So, Professor Vela is an assistant professor in the School of Electrical and Computer Engineering at Georgia Tech, and he's also an active member of the Institute of Robotics and Intelligent Machines. He directs the Intelligent Vision and Automation Lab, the EVA lab, where the research focus revolves around algorithms and algorithmic formulations for perception and control with application to robot autonomy. So his graduate studies were in geometric nonlinear control with application to biologically inspired locomotion. And his postdoctoral research involved a detour into computer vision, specifically controlled active vision and visual tracking. After becoming a faculty member at Georgia Tech, this line of research continued into the first few years. Emphasis was on exploiting the underlying geometric and functional representations of point-based and segmentation-based tracking for deriving real-time target tracking solutions. So currently, Professor Vela's group's research revolves around closed-loop aspects related to robot autonomy, with an emphasis on perception in the loop algorithms and the use of machine learning for control of robotic systems with uncertain properties or uncertain robot world interactions. So with that, Professor Vela, the floor is all yours.
Oh, thank you. Thank you for that nice introduction and for the invitation to come speak. The first thing, I guess, is, as was mentioned in the bio, I started off in control theory, and I'm fairly well versed in most of these methods, some not so much, but I understand them. And what I do now is basically how my research is a lot, how do we bring perception into the closed loop and make it so it integrates nicely with existing control methods. So I don't necessarily innovate on the control theory side, but I take all of the wonderful innovations from the control theory community and I say, how do we make these schemes amenable with what perception can provide? And that's pretty much what this talk about is how do we use perceptual information, is in particular in a navigation context, and how can we guarantee sort of collision-free performance of the entire system. There we go. Okay, perfect. So this talk is basically in 4 parts. I think the first 2 will be the longer ones. They sort of frame things, and then the 3rd and 4th are going to be a little bit shorter, and they're sort of like the consequences of the framing. All of the students below are basically the main drivers of the work. They do all the hard part, and I get to explain to you all the nice things that result from their hard work. All right, so let's move on to part 1, which is perception space and navigation light, so to speak. If we think about navigation, underneath it, there's a motion planner, but motion planning is not necessarily the same thing, because in motion planning, the idea is to create a path or trajectory through a specified environment, whereas the premise behind navigation is that one is maneuvering through that particular environment, and elements of that environment are unknown or uncertain, and one must respond to them in real time, right? So here, when we talk about a specified environment, the assumption is that it's complete and correct. So all elements of the environment are there, and all of them are properly modeled. Whereas the navigation system, what I consider is it has a partial map, which means that it's incomplete. So the premise is that some parts of that map are actually missing, or it's incorrect, which means some parts of it are not entirely proper. Maybe there's an opening where the map says there isn't, or there's an obstruction where the map says it's clear. Now, when we think about sort of these traditional schemes, they don't employ what I call perception space. They tend to model the world. So a lot of traditional navigation, or sort of the motion planning for navigation, is grounded in physical space. There's some kind of map of the world. What that map looks like is highly variable. These are just a few examples of those maps. Gridded, on the left, you have gridded. On the right, you can think of it as a collection of points where you take advantage of certain geometric properties. But there are also implicit representations. I think the main important thing is that it's grounded to an absolute coordinate reference frame. And then these different map models sort of lead to different computational trade-offs. There's the cost to build the map, and then there's the cost to access. And access is needed for collision verification. But when I studied computer vision, I came across this very old book from the 80s, work from the 70s too, on sort of the foundational aspects of computer vision, Marr. And Marr basically wrote this nice book that talks about the computational groundings of perception, from what are the biological substrates that lead to perception, but then what are also the algorithmic elements that those substrates necessarily sort of compute, and then how it's linked to perception. In this book, there's this notion of these different levels of scene interpretation. You have at the very beginning the input image, then this thing called the primal sketch, then the 2.5D sketch, and each is getting incrementally richer. There's more and more processing of the perceptual information to recover scene geometry, to recover semantic understanding of the world, and then ultimately ground it to some kind of absolute reference frame. So the traditional modeling spaces actually work all the way at the right, the object-centered, which sort of models things in sort of its full richness. Probably you can split that in half, but let's just leave it as is. But what people tend to ignore is this sort of viewer-centered thing. And why is this important? It's important because as you go along the hierarchy to this sort of object-centered, there's more and more computation, which means that if it's possible to push a particular algorithm closer to the input image side, then it's going to run faster, and it's going to have possibly more favorable properties because of that. And my research is really, how can we push these sort of navigation schemes to operate in this 2.5D sketch? And what benefits does it give you? Where does it work? What can you do with it? Things like that. What's important is that this is an image-based representation. So it sort of lives in this sort of projective space where things have depth layering. So you don't really remove the geometry as much as you model it slightly differently. All right, I described a little bit about perception space. Since it's image-based, it's very often going to, and projective, it's very often going to involve some reduction in your model representation relative to physical space. In a planar world, it's a reduction to a 1D representation. In a 3D world, it's a reduction to a 2D. So you're trying to capture a panorama of that world. What's important is, since it's viewer-centric, it also has to be propagated. So as the robot moves, this model has to move. So that introduces a little bit of additional computational overhead, since the other methods typically can just drop into a static map. I should have shown this earlier, but here's a good visual of what perception space affords you. Is if you look at this thing on the left, then what you want to do is you want to model the world not as this 2D that you view it, but sort of as, imagine these colored things are like a laser scan. Then what you can do is you can assess collision by saying, if a robot follows a particular trajectory, it must sweep out volume and space. And that volume and space is going to occupy a certain sort of segment of the laser scan at a certain depth. As long as the segments that are occupied and the depth that that robot occupies is at a closer depth than the world that's being modeled, then there is no collision, right? And you can see here that these lines go all the way up until this sort of colliding depth. if you propagate the information, then you can also retain the information around corners and behind obstacles. So this may not show that, but that doesn't mean it doesn't happen. Then in a 3D world, what you get is you get this projection onto a cylinder, and the cylinder tells you how far things are. And again, one can imagine if there's a robot, then the robot movement in certain directions or at certain poses is going to require carving out a certain sort of surface element in the world, and that surface element can be projected into sort of an artificial depth image that can then be used for collision checking. And this is what we choose to use instead. So there is no need to build a world model. In a certain sense, the perceptual state is the world model, and then you can use it immediately. There is a cost for this volumetric part, like looking at the surface for collision detection, but there are a lot of neat tricks to sort of make it computationally more efficient. Which leads me to my next point, is now that you've switched what this underlying representation is, it allows you to basically be a lot more flexible about how things are implemented downstream. And there's a lot of neat choices. What I want to look at first is, okay, what are the computational benefits of this perception space? On the left side, we have the perception space. On the right side, you can think of it as more this traditional raw data point cloud type thing. And in between, there are these two schemes for organizing the data. What you can see automatically, and then the traces are the number of collision checks that have to be performed for a particular sensor measurement. And then the y-axis is the total time of required to do those collision checks. What you can see is on the y-axis, the ones that organize data have a cost to build, right? I don't know if I have it. Nope. Have a cost to build, which is why they start higher, whereas the ones that sort of immediately take the perceptual data have almost no cost to build, but they may have a higher slope. So the cost to collision check is going to be a little bit higher. If we look at the traditional sort of unorganized, just assimilate it all, this can be used, and I think it gets used fairly regularly in robots or autonomous agents where there's plenty of compute, there's plenty of power, there's plenty of space to hold things. Then these ones that try to organize the data, if you look at it, they're very flat for low amounts of collision checks. What they're really good for, and they tended to be used early on when we started this research, was for micro vehicles, because those have highly constrained sort of compute requirements, just because it's a low power, low weight type of system. But there's pretty costly to build. Whereas in this perception space, since you're immediately taking the perceptual data, there's no cost to build. But there is a pretty high slope, but it behaves quite nicely. Now, if we limit ourselves to the regions that we care about when we talk about real-time performance, what happens is we're probably doing less than 1,000, maybe even less than 100 collision checks. And we want this to be done in at most 100 milliseconds. So this little box is that area. And when you look at it, then the perception space tends to be lower for a given sensor resolution than all of the other schemes. So when you want to do something that is over short time horizons that requires not so many collision checks, then this is actually the ideal sort of operational zone for the methods. Here's a video of it working. The video is not too impressive now, given what goes on nowadays, but I don't know if it's playing. Oh yeah, it's playing, but it was done 10 years ago on a robot that is the equivalent of, whatever the cell phones were back then. And what you see is there's a overhanging board on the left, which is, if you can see my mouse there in the middle, and then the robot is adequately addressing the fact that it's there, recognizes that it's in collision, and then maneuvers around it. A lot of the pauses are artificial. They're just to describe what's going on as the decision making happens. But this does basically volumetric geometrically correct volumetric collision checking in real time on technology that existed 10 years ago. I don't know, it was the equivalent of, I think, a Samsung, I don't know what was around back then, Galaxy 3 or Galaxy 4, something like that. So after that initial study, where at least we found that it runs fast and scales relatively nicely, then we had a question is, if we integrate this more richly into a navigation system, what can we get? So can we show that it improves navigation safety? Maybe provable. Does it support better, better performance, and does it enhance navigation robustness? And the rest of the talk is really about how we addressed at least two of these three. The third one, I'm not going to have time to talk about. All right, so next step is this sort of safety. How do we address it? And how do we integrate it into a full system? Traditional navigation systems, because they have motion planners, and motion planners over long horizons are not guaranteed to run in real time, they tend to break it into these, I call it three, but a lot of motion planners only do two scales. They'll do the global planning scale and the local planning, and usually the local planner directly outputs a control. But another way to think about it is the local planner may output a short horizon trajectory or path, and the role of the trajectory tracker is to safely track it. Very often, these methods will actually use the same map, even though, hold on, excuse me. They'll use the same map, and many people have come up with different optimal control or motion planning strategies to operate at this local scale. But if we look at the previous results, which sort of say that there's a computational advantage to perception space, what happens is some of these may have poor scaling properties because they're not taking advantage of a representation that's optimized for the particular scale that the decisions have to be made on. And our research says, okay, how can we alter these local planners so that they align with perception space? And that ended up being sort of this 10-year journey that I'm now describing to you, where the traditional approach is to take the sensor data, build a local map, integrate that into a world map, and then you have these two planners that are running, the global planner at a low rate and the local planner at as fast a rate as possible. If you can do sensor rate, that's great. If you do slower, that's okay. But the main idea is just avoid collisions. What the perception space says is, wait a minute, this local map, instead of being sort of in the same representational structure as the local map, as the global map, let's just make it different. Let's make it this perception space. All local planners tend to follow this relatively generic framework of identifying what are reasonable goals, identifying what are paths, scoring those paths, and then executing the best one. And what we want to do is sort of percolate. If we're using perception space now, how does perception space fundamentally alter everything downstream? And then this connects a lot with MAR, because once you've changed your representation, you fundamentally have to change the computation. And hopefully all of the benefits that we think are going to happen will actually happen. This is Teams. I don't really know how Teams works. In the Zoom, I asked the question, what kind of decisions do you make when walking around? What do you think is important? But I don't know. I don't know how to see the chat in Teams. So if anyone wants to chime in with the chat or what they think, they're welcome to do that.
Can you access the chat on the right-hand side?
Oh, I see it. I see it.
Yeah.
Yeah. Or if nobody wants to say anything, then they're welcome to stay quiet.
Depending on the environment and how much information I have, or if it's icy, I will go slow. Or if I can see far, I might go fast. If linking it to the perception side, my prior model and my sensory inputs are coming in. If it's too different, I will slow down to get more measurements. I think so.
Okay. Now you focus there on speed. What about how do you know where the thing should go? Like how do you decide where to go?
Yeah.
That's so okay. So
Historical, but yeah, no, yeah, there is no.
Uh, I make a mental model of like predict some sort of like where the environment might be going or something like that, and then perceive whether my actions are going to intersect the position of obstacles or something. So I do make like small horizon predictions.
yeah, exactly. So what those are good things. But what I'm going to bring in now is not only Marr but Gibson. So Gibson was a contemporary of Marr, and Gibson came up with this notion of affordances and says, let's think about sort of agents and their decision making. It always happens in the context of an environment. Like an agent is their state is not simply the state of the agent, but the state includes the world. And what affordances or what action possibilities exist for the agent, they're fundamentally dependent on the world, right? So there's this coupling between sort of what agency an agent has, but what agency it can actually execute. And in that coupling is with the world, right? So if you look at what Mars is sort of giving you this idea of how computation and perception should be linked. Uh, Gibson is saying what should be the primary consideration when thinking about the agent and the world as this unified state, or what should the perception system be cueing on when the objective is to navigate the environment. And what Gibson then says, if you say, okay, I want to put Marr and Gibson together in my navigation system, then the way it works is there'd be this perception space map, then there'd be this affordance analysis. What is perception? What are the perception information telling me? And what is critical in that sensory information regarding the task that I need to do? So the emphasis should be all computation should be geared towards solving the task. And there should be no excess computation trying to do anything else. Then that can then support, in principle, if you do it right, local planning and then control by the robot. So what we discovered is that then there's this process, which is you analyze the vision data, build your structure, identify the opportunities using this idea of affordances, then you pick from those opportunities and then you execute. And the main affordance that we sort of came up with is the idea of gaps. Now, gaps have existed in the literature, and what's interesting is that gaps, you can think of them as depth discontinuities in the space. So the fact that they're depth discontinuities works very well with Marr's hierarchy and this egocentric approach. However, the way these gaps were organized didn't seem to make sense from a Gibsonian perspective. So what we did is we sort of analyzed them and said, we have to come up with another scheme for how to define these gaps. And what makes them important is that you can think of gaps as these are directions of travel that are collision free. If you move towards anything that's not a gap, that means you're moving towards an obstacle, right? And so when we think about affordances, the reason gaps are natural affordances is because they're giving you an opportunity to move that is collision free. And that opportunity, or an opportunity to sit still, right? and do collision freeness. What's also nice about these gap-based methods is that they're very often reactive. So they actually live in the short time horizon, short spatial scale system. Our approach to gaps is to find the depth discontinuities, like many of them do, but then to also try to simplify them and to understand what these depth discontinuities meant. If you look at them, a lot of these depth discontinuities, they radiate outwards from the robot. And those are not particularly good things, because if you were to cross that particular line, that gap, which are the red lines here on the leftmost image, then they take you from an area that is fully visible to an area that is occluded. And that's not a good idea from a safety perspective. So what we did for our notion of gaps is to say, wait a minute, we need to find the gaps that are swept, that have more of a angular, but they have a larger angular rate of change than a depth rate of change. And so there's a process that takes these depth discontinuities and tries to recover geometric structure that says, wait a minute, in order to go around and cross this red thing, you first have to pass between these two things. And so the gaps that have this pass between, they're kind of, we call them swept gaps. And after the simplification process, you may still end up with an unmerged or an unsimplified gap. Then the third step is to say, okay, that's the only way to go through there. So there's a little bit of topological reasoning here about this processing of gaps. I'm not going to cover that, but we did exploit that topological reasoning early on in our research. But the ones that maintain their radial nature, we have to rotate them. And the step 3 shows how you sort of take it and you rotate it inwards to become more of a swept gap. So what you get now is you get this line of sight visibility of free space regions of the robot that are opportunities to move, avoid collision, and advance, right? Anything that moves, not anything, but most of the time, if you move towards an obstacle, you're not going, at least in this local model of the world, you're not going to progress towards the goal. Then if you look at them, they actually define a star convex region. This is not important from this perspective, but when you combine it with optimal control, the fact that it's star convex is important because some algorithms rely on convexity for performance improvements. And the fact that this is star convex means that if you define a trajectory properly, you can actually find a convex subset for the optimization problem. So this is where our perception and computation fundamentally sort of support better computation. All right, so now navigation basically says, let me identify the gaps, and then each of these gaps is an opportunity to progress towards the goal. If the goal is not within the convex region, so this sort of, there's like a convex hull, if it's not in that convex hull, or you can't see it in the star convex shape, then you're going to have to pass through one of these gaps to get to the goal. So the local planner has to then decide which one of these to cross. And then once the planner decides which one to cross, the planner then has to say, okay, I have to identify a path that is region invariant. So the path must stay in the green area. If I can guarantee you that a path stays in the green area, then I can guarantee collision freeness. And actually, the green area, normally we shrink it a little bit to avoid collisions, but this is not the true collision-free area, but there is a smaller one that would be the green. And then once you've identified what this region is, then you can say, oh, I'm moving towards this gap. I can find a subset of that star convex shape that if I navigate, I should stay within this subset. And this subset has nice properties from, again, motion planning perspective. All right, let's go back to our 1, 2, 3, 4. So the perception space and Gibson tell us we want to model the world locally in this perception space. We want, during the modeling, we want to capture gaps and then use these gaps as affordances that tell us how to navigate safely through the world. What you should notice is that I have, even though I've talked about navigation, I haven't described how we do our local motion planning. And the reason is that as someone who's from this control community, and I see that there are, dozens of solutions, everyone's always publishing their favorite motion planner, optimal controller, is I'm trying to describe this in a way that is to some degree agnostic to the computational solution that is doing this optimization, that is solving the optimization problem. And then if I can do that, then I can basically take any existing navigation system, drop this in, and in principle, it should be improved, and I should be able to make conclusions about its performance. So one conclusion that we care about is what I call this provable safety. What I described earlier is that safety is going to hinge on identifying a collision-free region of space around the robot that can result in if the robot stays in it, then the robot will progress towards the goal in principle and not collide. Notice that if I can find this region, I have to do no collision checks in the region. I basically am guaranteed collision freeness within this entire region. So on the left side, what we started with was what I call the gap sector. It's sort of just this triangle between the robot and the two gap edges, which we call the left and the right gap. And then that red arc is the gap. I think that's what we call the gap edge. Now, the left side is what works best for the ideal holonomic robot, which means that in the holonomic, even though the robot is vectored, like if you look at the direction that it's pointing, is not in line with the sector, a holonomic robot could still move into that sector without any problems. Then the one on the right is sort of how can we extract the largest possible region, but still retain some computational simplicity. And what we first started was if we could find the circle that has the nearest obstacle, then if the vehicle had to be vectored in the direction that it was pointing, then one could create a slightly different triangle, a slightly different gap sector by pulling it back, but still staying within that particular circle that's collision free. You'll notice that when you pull it back, it closes in the gap edges. The left and right have to close in a little bit. So you're kind of sacrificing collision-free volume in front of you to increase the collision-free volume around you. But now if you do this keyhole, now the nice thing about the left two is that they're convex regions. On the right two, you have more of a star convex region. And the idea is to open it up as much as possible to enhance the convexity, or how much of that space sort of is star convex versus convex. But what happens is this basically, if you can create these regions, they're guaranteed collision free. So the very minute your perception space system has built its model of the world and has analyzed the gaps, which is sort of in a planar world, this is order n. It's blazingly fast. Then you automatically get collision freeness. So our first sort of provably safe navigation scheme said, okay, we have a holonomic region. All we have to do is use these flow field methods. So there are methods that generate flow fields, and then they have these guarantees on the flow fields and their performance. So we took those ideas from the sort of control literature and said, okay, if we have an ideal robot, it's a point mass, it's a first order model, we can see everywhere around us, then this kind of model guarantees that that the robot will never crash if the flow is designed properly. And here's sort of a depiction of it navigating through space. And you can see that the yellow things are the gaps. Then the blues are the gaps, define the gap sectors, all the rays that emanate from the robot. And the purple line is the trajectory that's chosen. And then this scheme works very well. It's fast. And what we do is, in my world, I like to simulate things because we can reproduce the idealized model. So there's this nice simulator called STDR that allows you to model exactly first order motion, full 2D control, full 360-degree scan, point mass. And when we run it, we basically get no collisions across a bunch of benchmark worlds. Now we can we can get rid of one of the things, which is the full field of view. And then now the guarantees go away because one does not know the environment. It's a partial understanding of the environment. And then you can see that some collisions happen, but there are less collisions and the success rate is much higher than for sort of the best competing system. And then once the field of view gets low enough, everything just fundamentally degrades. So what I find fascinating about this is the 120 is roughly the human field of vision. So I don't know if that's an accident or not, but you can think everything is great all the way to 120. and then it just degrades. What humans have the benefit of is a neck. Our robot has a statically placed camera. It doesn't have a neck. But you can sort of see that I'm not giving you the proofs, but the main essence of the proof is, can I guarantee that there's a path that's collision free, which I showed you you can, and can I guarantee that I can make it past that gap sector that my flow has to leave? And then the paper goes over the proof of why that must be the case. Now, if we get rid of some of these things, so this is now a non-holonomic robot, we have to do this radial extension that I talked about, where you extend the triangle, but you sacrifice some things. And then we can then get very close to zero collision rates, but not quite zero. Just because the theory no longer really holds. And then we can also implement it in simulation. And we get some collisions because the theory doesn't apply, but we get much better performance properties, even though the field of view is quite low, and control feasibility is not guaranteed. All right, so what can we do if we don't have ideal robots, right? So a lot of my work in the past, let's say 6 years, has been, how do we relax the assumptions that underlie this? And as we relax our assumptions, we rely on more and more sort of complicated, sort of optimal control or motion planning methods to address the complexity. So one thing that we did is, well, robots aren't point masses, they have volume, and we have to take into account the swept volume as the robot moves. For us, what we said is, well, we can treat it as a diagonal length and just create a radius that's much larger, but that becomes conservative. Can we instead take into account the fact that as the robot moves, there's going to be this canonical width for the robot that represents the worst case scenario if it moves in that direction. And there we came up with this idea of an equivalent passing length and an equivalent radial length. So the passing length is if it's vectored along a direction, but sort of based on its orientation, what is the effective width? If it just moves straight in that direction, what is the effective width of the gap that it would be able to move through? And then we also have this thing called the equivalent radial length, which is, what is the distance from the nearest point of collision of the robot when it moves in that direction to the furthest point of collision in a sort of polar space? Then what that basically does is that defines a way to assess collisions in this perception space quite rapidly. And you can compute this equivalent radial length and passing length offline. So on the right, you can sort of see this surface reconstruction of what that equivalent length is. That's based on the geometry of the robot. And then we can then incorporate that geometry into the circle and the gap sector. So here we have a technique that I think Naira has used for optimal motion planning, which is to deconstruct a path into these sort of Bezier segments. And the Bezier segments are very nice because as long as the nodal points, the path that is generated from a Bezier curve is always interior to the convex hull of the nodal points that describe the Bezier curve. So then we come up with a scheme that, given the direction that the robot is facing and sort of certain constraints on its motion capabilities, we can then define Bezier, a set of control points that lie entirely within this keyhole region, and that then will generate a path completely inside of it. And again, we do simulation, where here on the left, it's sort of the idealized. I use STDR, I love it. And then on the right, we sort of make it increasingly more realistic to see how the performance of our navigation system degrades. My bad. So here we have this thing called Ridge Dog, which I totally love. We took a quadruped and gave it a sort of virtual holonomic base, and it just moves around like that. Whereas the regular dog moves like a regular quadruped. And then we run it through these benchmarking. You can see there on the right what it looks like for sparse environments, and these are slightly denser. I think if you can see it, hopefully you can see the 60-degree field of view of the robot. So it's, even though we can see that that path may not be optimal, it's not the best path. I mean, you have to realize all it sees is 60 degrees in front of it. So it has horse blinders. And a lot of the oscillations you see have to do with the partial observability of the world. So it moves where it thinks it's safe, but then it observes things and then it has to adjust. So what are the results? The results are that in STDR, we get full success rate, no collisions. But then as we move towards the ridge dog, actually, we still get no collisions. But then when we put it on the real legged robot, we get this drop in performance that's fundamentally derived from mismatch between what the hybrid legged system can do and what the continuous approximation of that system is. But if we look at sort of how, let's say, TEB, another system, works, you can see that there's a much bigger gap in performance between the easy and the hard environments, whereas ours has a much smaller gap. So that says that this sort of perception space gap-based approach is paying off in terms of being able to hypothesize good collision-free trajectories. And then here's sort of a little bit of it in action. This was one of our very first, well, I don't know how long ago, this was 5 years ago, maybe 4 years ago. When we first were playing with these quadrupeds, you can see they're tethered. We've recently untethered it, but you can see that the perception space one was able to assess that area between the trash cans was safe, whereas the tab unfortunately could not. And then we compare in these sort of small environments, and what we can see is that we get much better performance than tab. All right, so now if we go to a non-trivial motion model, here we have non-holonomics. So now non-holonomics are a little bit worse because we cannot vector in the direction of the gap sector. We must vector in other directions. And so that's where we use this full keyhole region. The reason that we want this full keyhole region is if you look at the dark gray shaded area, what you can see is that it doesn't look like a circle with a gap sector, but where the QL-inf and the QR-inf is, that we've expanded a little bit. I call that the armpits, where the sector, where the two lines that radiate from the robot intersect the circle. That little area, I call it the armpit. And what we've been able to do is we've been able to open up a little bit more space in the armpit, because if the robot is maneuver constrained, that armpit is always where the robot's going to end up. So we define this new region called the keyhole region. And again, we come up with very fast ways to generate this keyhole region directly from our perception space. Once we have it, there's no need to do collision checking, right? So, and then what we do is we come up again with another Bezier curve approach to synthesizing this. And the Bezier, I think if you specify properly the velocities and the positions, it becomes a fully specified problem where all of your Bezier nodes are completely determined. And that's kind of what we did here. And then at least for path synthesis, then what we did, I'm not going to cover it, but then we come up with the machine learning strategy to generate a level set function that recovers this region as a level set, so we can then use it as a barrier during the rollout, and this barrier will guarantee that the system doesn't collide. Because if we go back, this thing guarantees path, so it guarantees collision freeness of the path, but it doesn't guarantee that the path is necessarily control feasible, right? And then what we have is this zeroing barrier function that allows us to understand when the collisions are going to happen in this sort of forward motion of travel through the gap. And then those get integrated into like a nonlinear model predictive control motion planner, so that we can then sort of assure safety of the rollout. And then here's an example of the system moving through the world. And as it detects the obstacles that are not in the map, you'll see them pop up. And you can see the gaps and the keyhole that's taken. The gap that's taken then has a keyhole generated for it. And then you can see that the robot then uses, I think it uses a discrete time model predictive control formulation to identify the short-term horizon path. And the same zeroing barrier function then gets used to assure safety of the overall robot. And then here's sort of an ablation study. I'm going to go through it a little bit fast for time. I think the important thing is the last two lines. So you have the SG, which is what we call this, what I just described, safer gap. And then the original one, which we call potential gap with the projection operator, which is a form of a safe barrier function. And you can see that, and this one, what we did is originally we had very little collisions and then we just kept running it. So I think the bottom two rows are like 5,000 or something like that trials, whereas the ones above it are maybe around 1,000 or 2,000 trials, just because they were statistically significant in difference. But the lower ones, we had to keep running it until we got a statistically significant difference in collision rates. And then that tells us that the safer gap approach is much better at addressing sort of these non-holonomic constraints and sort of giving you control and collision feasibility, if you will, or satisfaction. And here's an example of it running. I'm going to try to finish in the next 5 minutes. And this robot is a kind of a great robot and a horrible robot at the same time. It's great because we can implement everything on our robot, but it's horrible because it doesn't drive particularly fast, and it has, I think, a 10 hertz constraint on sort of how you can actuate. And our algorithms can run very comfortably at like 30 or 40 hertz, but we're not able to leverage the speed that can run at. All right, so what does the gap afford you? What can you do? How can we go beyond what's here? So one thing that we've been studying the last, let's say, 3 years has been what happens when they're dynamic agents. Now these gaps are they're evolving in time. Now, what's interesting about this gap-based approach is if you remember Mar's visual hierarchy, the hierarchy said that the very last stage was object-centric. At the viewer-centered, Mar would say there is no notion of objectness. I don't know if that thing in front of me is a couch or a chair, if that thing that's moving is a person or something else. It doesn't matter, right? And not caring about what it is significantly saves you time. And but it also provides these limitations on what you can do. So we take the idea of let's not recognize anything, everything is moving, even static things can be moving. If you have a limited field of view, a long infinite wall will look like something that's moving. We don't care about that, right? So this is but what we want to know is how far can we get with this very constrained notion of the world and how we should move within it. Again, what we want is free space. So for those who are aerospace people, you might like it. What we did is these gap sectors, you can think of them as if I follow that line that is the left and right edge, I will collide. The robot follows it, the robot will collide. Now, if that edge is moving, what we can do is we can use missile guidance laws to induce a collision, and that will partition my space more from a trajectory perspective or from a control perspective. And I know that any other guidance law that steers me to the right of a left gap and to the left of a right gap is guaranteed to be collision free. So you can actually augment this notion of gap and think about it as I'm trying to collide on the left and the right, and any control policy that steers me interior is guaranteed to be collision free. So we take advantage of that to then derive sort of theoretical support for that if there are two agents in the world, or if there is a gap and it's closing, we can guarantee that it's collision-free as the robot moves through it, even though it is moving itself. And part of that involves assessing the gap. And here you see these 2 points on the left. There's four pictures of the 4 different robot poses. And the important thing is the gaps can be opening or they can be closing. And do you look at sort of the part that's outside of them or the part that's inside of them? And then they can also be moving transversely. I don't show that, but they can. The important part is the open and close as opposed to the transversal. And then we also just come up with this constant velocity estimator model for the gaps. And then we have theoretical support for a holonomic vehicle to be collision free in this space. And then this is kind of like a picture I like because you can see all the way on the right are the dynamic gap approaches that we have, and they have a very high collision-free properties. The reason that they're not perfect is because the agents in the world are sort of random walkers. Sometimes they don't satisfy the constant velocity model, and they don't care about the robot. So on occasion, when the robot is near it, what'll happen is the agent will suddenly veer, and then that sudden veering will move into the robot, and the robot really has the robot can't avoid it at that point because the agent has both redirected its vector and accelerated at the same time. And that's why you don't get 100%. There's also some minor visibility issues, like if some agent comes around the corner. But what I think is interesting is all of these other methods, they do fairly bad. And some of these are learning-based methods. So what we're finding is that learning-based methods don't really perform particularly well when it comes to navigation. They're quite horrible. But there's still opportunity because there's a big gap between the holonomic motion and the non-holonomic motion. And if we look at what I like about this too is that the vertical axis is time and personal space. And there's this large literature on social navigation and coming up with metrics that are good indicators of, am I being a good robot in an environment full of people? And what we find is that the better something performs according to social navigation metrics, actually the worse it performs. So there's like this negative correlation between good behavior and performance, which may indicate that sometimes you just got to be a little naughty. But that's also an opportunity because how can we make it more socially aware while not degrading performance, right? Nothing lives in the bottom right. Where you see an emptiness at the best performing area, there's an opportunity to do research. We've also extended it to aerial navigation, where we define a collision perception space model for aerial vehicles, and then we can use it to identify gaps, and then we can collision check by projecting aerial vehicles with non-trivial geometries into that space to assess for collision checking. What we get is again, very nice sort of collision checking performance properties. This is roughly the same region, the yellow region from before. And then here we have some lightweight benchmarking. This is our first result in this area. We're trying to extend these results. So there's an opportunity. We can improve the method. I think our method doesn't really differentiate between sept and radial, and some of the collisions occur because there truly should be radial gaps, not swept gaps. And I think we can use the ideas from potential gap to provide theoretical guarantees that this thing should never collide. So these are directions of future work. And then finally, one thing that we're coming up against is that this gap-based navigation is primarily path-based. So it guarantees that the path is obstacle-free, obstacle-safe, I guess. But what it doesn't guarantee is control feasibility. And I think if you look at the literature, a lot of the community is really enamored of these methods that operate in control space. They work quite well in sparse environments. But what happens is that since the path is not guaranteed obstacle safe, but it's sort of guaranteed control feasible, as the environment gets denser, a lot of these paths end up being rejected. So what happens is you get this sampling inefficiency, that the sampling degrades over time in these highly constrained environments. And I think there's a gap between, no pun intended here, but there's this space between a path-based approach and control-based approach. And there needs to be a way to get these to kind of operate well together. How do you come up with something that has the best of both worlds and it runs blazingly fast and sort of can inherit the guarantees that the gap-based approach provides? In closing, basically what we started with the research question is if we believe MAR, computation, and perception are intimately linked in order to do tasks, and we believe Gibson, then we should be able to do very well by looking at these perceptual representations, by doing viewer-centric framing of tasks that make sense in viewer-centric modeling. And what we've shown is so far that this actually is quite beneficial, that it runs fast, it's provably safe under ideal models, and we're increasingly trying to make it work well for these non-ideal models. It has high task completion relative to the baseline methods. Almost every baseline method can be extended with perception space. I think that's something that's super nice. And then I didn't present it, but we can also enhance navigation robustness. And so I think the take-home message is perception space is great if there's an opportunity to incorporate these ideas into anything you do over short horizon, sort of the star convex regions of the world. This is something you want to be doing. That's it.
Thank you so much, Professor Vela. So yeah, if anybody has questions, please raise your hands or just please go ahead, and then we can go. Okay. Yeah, Vivek, go ahead.
Hi. Hi, Professor Vela. Nice talk. I learned a lot actually. I had a quick clarifying question or something like about how would I do this affordance analysis? So I think the part of the talk was that you take the perceptions, the outputs from the perception space, and then for the local motion planner, there is some sort of an affordance analysis going on, and then there is a path that is generated, right? So I guess my question is isn't there like a number of samples versus time space, the sampling versus the time separation kind of issues that come in this? Like, for example, how many samples are we getting every time when we are doing from, let's say, when the robot is moving? Ideally, we slow down and we scan the environment and then take actions. Is that what the typical way of implementing these is, or how does they get implemented
I'm
in the
not,
bigger
I'm not
autonomy?
certain what you're getting at here, but what happens is that there's this, trying to see if I can get a good picture, but all of these pictures that I show you with the gaps,
Mm-hmm.
like kind of here, like what you see is you see this laser scan.
Mm-hmm.
So you see the white dots,
Yes.
right?
Yeah.
Now, if this is a laser, you get it directly. If this is a depth image, what we can do is we can actually convert the depth image, assuming it's a depth image in a planar world,
Yes.
we can
Uh-huh.
convert it into an equivalent laser scan that says if the robot moved in as a straight line in this direction, it could move all the way up until this pose,
I
and that
see.
will be a collide, right? So what you
Okay.
can do is you do immediately, like directly from your depth image, you can generate the equivalent of this laser scan,
Uh,
which is a collision-free direction of travel.
okay.
Then once you've generated that, we process that for the gaps. And once you've got the gap, that's a guaranteed collision-free region up
Okay.
to the accuracy, like the resolution of the sensor, right? So
Yes.
depth images, what depth images do is they have they have a small field of view, but they have very high resolution within that field of view, right? I can have
Mm-hmm. Mm-hmm.
640 pixels across, and I'm only looking, let's say 60 degrees, or let's say 64 degrees. So I have a 1/10 of a degree resolution, right?
Yes.
But what happens is if up to the resolution there, you can guarantee that it's collision free. If there was something that was a tiny spike, right, that was right in between sensor measurements, this can't guarantee collision freeness, right? So
Okay.
there is like, you can think of it, there is a Nyquist sampling criteria
Yes, I
type of
see.
thing for these guarantees.
Okay.
Right. And I
Okay.
think we stated in the papers, I don't necessarily state it in the presentation, but
Okay.
definitely if you observe it, you know, if there are limitations on your sensor, then you have to be aware of those.
I see. I see.
But I mean, it's rare that the environment's going to have that. And if the environments do and you expect it, then you have to create a processing scheme to be able to detect them.
Yes. So just a very small follow-up. So this seems like, oh, okay, Aditya will go ahead and then I can.
No, 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 go ahead. If it's a small follow-up, go ahead.
Yeah, I just was like, this seems like a predictive thing, right? Where you can look and then predict in the future and then move along that direction. But you also said something about it being reactive, that if it can switch directions. I think is that
Um,
something like when you get like something changes in the environment, these lasers will switch and then a new gap will appear, and that what is meant by reactive?
I'm not, I think I definitely used the word reactive when I was describing the gap-based methods.
Okay, okay.
The original research in this area, and by that, what reactive meant is it just you know, like in the potential field method is considered reactive because you collect your data, you build a potential, and then you follow the gradient. And
Yes.
then you just keep doing that over and over again, where the gradient has both, you know, task completion and collision avoidance encoded into it. So when I talk about reactive in that context, it just means that the original methods were reactive, which meant that they were intentionally designed for short horizon, sort of
Okay.
short spatial scales.
I see. Okay.
Right? But what we're doing now is we're trying to have a little bit more of a deliberative process to actually hypothesize paths or synthesize trajectories within so we do a little bit more analysis. Those original gap methods don't do as much analysis because
I
it was
see.
not relevant to their particular solution. Whereas within a navigation system, we need to guarantee certain things about the local planner. So we have to do some additional computation.
Sounds good. Yeah. Thank you so much. Yeah.
Professor Vela, it's 11, but if you have time, I would like to ask questions. Otherwise, I can always, me and the others can send you an email. What would you prefer?
I'm fine here. It's lunchtime now, so I have nothing planned. I'm
Oh,
okay.
okay. So then I won't take much time of yours, but just following up on what Vivek basically was saying. So I might be repeating the question, but uh, when you do the dynamic gaps, the dynamic navigation, there did you come to that point where there's that fundamental limitation, like a Nyquist sampling, but for the environment and the system, that the environment has to be uh, some rate below my system, otherwise I will never be able to guarantee collision free. So I need to be faster than my obstacles basically, or I need to react faster than my environment is moving to be safe, to
Yeah,
be
we
collision free.
haven't. I'm with you on that. We haven't dealt with let's say agents moving 5 times faster than the robot, so it can't get out of the way, right? Like I think most of the time when we target this, I think the best way to think about it is if you looked at the way I develop, I'm very conservative. I start with an ideal model. I try to show something. I try to then create a benchmarking simulation that reflects the ideal model. And then I try to degrade that. I would say that our dynamics, the dynamic worlds that we consider, are what I would consider to be, they're not really ideal, but they're as close as you can get to idealized dynamic worlds in that they involve agents that move roughly as fast as the robot itself, right?
Okay, that's excellent then, right? If the agents, I mean, I would imagine if the agents are faster than me, then I cannot guarantee collision.
Yeah, exactly,
Roughly.
exactly.
So I guess your results are basically tight in that regards.
Yeah,
Uh,
for holonomic, but what happens is they're only guaranteed if you're looking at a two agent interaction. right?
I
But
see.
I
I see.
don't have the videos because I couldn't find them. The student put them somewhere where I don't know. But basically, if you now have a world where there are like 50 agents, then what happens is I can guarantee this system can guarantee that for its local setting, if it decides to go between two robots, it's guaranteed to make it past them. But once it makes it past them, there's another configuration of the world beyond that that may involve robots converging into the where the agents converging to where the robot is going. And then that could create a situation where the robot actually cannot avoid collision. So what
Yeah,
happens is you
yeah.
can think of this as it's guaranteed when there are two agents. It's not guaranteed when there are like 50. There are loose guarantees when you have 10 or 20, because what happens is they're so sparsely situated in the world that your robot is only ever encountering a two agent situation.
Yeah, okay. No, that makes sense
Right.
actually.
Yeah.
Yeah, because then after that it becomes ill-posed. In that case, maybe the agents or the obstacles are slower than you, but yeah, they can corner you,
Yes,
and then
exactly. They can corner
it's
you.
infeasible.
You can be trapped.
Okay.
And what we're trying to do is, I think, I'm not certain, but what this is it's basically converting a combinatorial optimization into a smaller sort of finitely sampled optimization problem. And I suspect that what we might be able to show is that we're computing a greedy solution to this combinatorial problem. And if this motion planning problem is submodular, then we can show that this greedy solution is near optimal.
Hmm.
We can't, again, we lose guarantees of collision for like collision avoidance, but what we may be able to show is near optimality of the decision making, which means that we do a good job at avoiding things that would lead to collisions, if that makes sense.
Yeah, that makes absolute sense, especially intuitively. If it follows it, then everybody's happy.
Yeah.
One small question, I think you might have talked about it, but just for clarity. So in the hierarchical approach, which again makes all the sense, you have different mission planning will obviously be the slowest, and then you have the
Mm.
local, and then the high rate. So there is that link between the global map and the what are the terminology of your
The perception
the
space map.
perception space map exactly, and then they were feeding into each other. My question was, how are they interacting? Because I remember you mentioned the downstream from that, but there's also this upstream interaction between the local and the global map, and therefore also it seems like the solutions are locally optimal. So what are the conditions that, again, what we were just describing, that you don't get cornered, or there'll always be a path because you're doing locally moving towards the gaps. You don't want to run into a local optima, I guess. Um,
Yeah, so I would say because the problem is that we're navigating unknown worlds. I don't think there's anything we
uh,
could ever guarantee about being globally path optimal,
that makes sense.
right?
Yeah, that makes sense. Yeah.
Yeah, and I think I'm not really certain what I would love to do, but I don't necessarily know how right now, is I would love basically what we're showing is that motion planning, there's this idea of task and motion planning, right? Where you have these discrete tasks and then you have these continuous motion plans that try to bind together to discrete tasks. What I think we can show is that this navigation under a hierarchical navigation problem, it reduces to a task and motion planning where the task is to identify what is the best gap to pursue now, and the motion plan is the path that we generate. And so by showing that this motion plan is guaranteed safe and to show that the task is progressive in some manner, then you can, in a sense, show maybe that you can guarantee that at the task level, it must go to the goal if there's a path to the goal. So there's this idea of from computer science of is it decidable or can you compute the solution? And what I would love to show is if the path is feasible, does this guarantee that you will actually find a series of task level decisions that will lead you to the goal, right? So
Yeah. That makes sense, and I think if in aviation we also have we use this example. Naira knows this about the example of the Captain Sullenberger ditching into the Hudson, and that we were using as an example of him. He chose the task which was feasible, which was not to go to the airport, but to ditch on the river. And then the motion planning was to take that aircraft into the river, and that same hierarchy shows up, which is really interesting. Um, I have other things, but yeah, Naira, do you have Naira's here? Just wanted to because she's been.
Ramona,
Naira, you're
sorry for
muted.
being intermittent. Some calls run into conflict. Patricio, thank you for presenting for us, and we're happy to collaborate meaningfully, not just give seminars at Georgia Tech and at Illinois. So we can make
that'd be great.
Because I was thinking on that exact thing when you were using the motion planner not being a control feasible, or the motion planning is generating trajectories that the system will not be able to follow, something along those lines. And you're saying when the environment is cluttered, of course, your sampling becomes inefficient because most of your paths will interrupt. You have to reject those. So if we kind of use this, or I mean, we don't. It's a well-known thing about like tube control, tube planning, where you have your system, you don't know much, but you're like, okay, if that is my plan, I will remain in a tube around that plan. So I was wondering if that could be the dynamic gaps for the perception coupled to these, I would say, the local plan-centric gaps, because these tubes can be thought of gaps that are clamped on to whatever the planner is saying. If the planner says go their route, this dynamic gap for the controller goes there. Um, that could be something like, I mean, I need to read much more because I come across as an idiot otherwise, but just thinking high level, that sounds like I'm very interested in this gap. But basically, that's what I'm saying.
Yeah, I mean, I agree. I think there's something to be said if it's possible to find how these star convex regions intersect with tubes, right? You want something where the intersection of the tube with the region preserves the entire volume of the tube. And if you can rapidly assess that, then that provides a mechanism to understand what's feasible.
Yeah, that's exactly like in our case, there is no obstacles are fit. We know that, so all we have to do is the tube is outside of the obstacle. But now it is tube intersection with this gap, and
Yes,
of
and
course
I
the
think that's
question is,
there is a lot of value to thinking of it as tube intersection with gap. I don't have stuff here. I don't have it in the presentation, but for the MPC solver, what happens is MPC solvers are kind of horrendous because every obstacle you must avoid it, right? So if you think about the optimization landscape, every obstacle carves out, it cuts out a chunk of what's feasible, and it creates all these holes in your decision space. And now you have to find your way through these holes, but it's non-trivial if your initial guess is bad. Whereas what the gap-based approach does is it sort of says, look, if you know you want to travel in this region, here's a very nice here's a very nice subset of the space that has no holes. All you have to do is find a path that is invariant to that region. And so
yeah,
it makes the problem much easier. Like let me go back. So it makes the optimization problem easier because you have a single unitary constraint for region invariance, as opposed to if I have 7 obstacles, I have 7 constraints that carve out space. So there's this insensitivity of the computational demand to the specification of this star convex region.
that actually, yeah, that's a big gain in computation, because at the end it's always one constraint, regardless of how many things are going around.
Yeah.
Okay. My final comment, Professor, is like your research did reveal some really nice things when you're saying you have to be a little bit non-social, antisocial to be performing well. And I mean that works really well for engineering students too, social skills and being always working. And then on your slide 57, your quadruped, that had a tether. You were saying now you have removed the tether, but it had a tether on it. What was the purpose of the tether?
Oh, the tether, it's a good question. I think I think it may have been some of the compute because
Okay.
these robots don't come with a particularly good compute module.
Yeah, that makes sense. Okay, yeah,
And
no.
it didn't really have to do with the perception. My collaborator, they do whole body motion planning, and I think it had more to do with maybe the motion planner or something. I don't know exactly.
That does sound likely
For the
because yeah,
Liget.
that'll be running. Yeah, okay, that makes sense. Uh, Vivek and Naira, and I think Petros is here. If you have many more questions, please. Naira, then you can say please the closing remarks.
Nothing from my side. Nothing from my side.
Thank you,
Prof.
Patricio. I'll go over the recording. Sorry, had to miss, but I look forward to establishing more robust collaboration in terms of really generating new impactful work with meaningful results. Maybe writing joint proposals, maybe doing workshops together in some conferences, because I think you talk the control language well enough so that we can work with you and use some of your computer vision algorithms with our solutions.
Oh yeah, I think that'd be exciting. I think that'd be great.
Aditya will assign students to you.
No. I think this is what I was going to say. Both Vivek and I will actually read because the ideas seem to be sitting there, and there's so many good things like the your approach being agnostic to the motion planners, I believe you're trying to keep it as agnostic as possible. That's one of the really good properties that we are also looking for, and so I think both Vivek and I will go through these papers. Let us see what we can figure out, put something in the language of yours, and then reach out to you, and hopefully our ideas will be worth pursuing.
Yeah, absolutely. You can, you can always schedule a meeting in, a couple weeks or something like that, and we can talk about these things.
Absolutely. So we'll reach out to you. Let us quickly go through at least these few papers to get the terminology up and get the methodology down, at least enough to figure out like how the merge point can happen and what we have, and then questions and request meetings with either you or your students, of course.
Cool.
Thank you. Thank you. Bye.
Thank you so much, Prof.
Thank
Bye.
you.
Bye-bye.
Yeah, just share the slides with me, Patricio, and I will send you an email with the link of where the video, your slides, and everything will be.
Sounds good. You want me to show them as a PDF? Like, is that?
Yes, please. Vivek, right? PDF, right? That's
Yes,
on the
PDF
website.
would work best. Yes.
Okay.
Perfect.
I'll do that.
Thank you so
Thank you
much.
very much.
That's a wonderful talk. Thank you so much.
Bye-bye.
Bye.